Willow, what is the derivative of sine?
Cosine.
Good job! Willow got us started. We are going to be learning about the graphs, bye baby, for position, velocity, and acceleration of a system oscillating in simple harmonic motion. Now, it's really important to remember that simple harmonic motion occurs when our restorative force is linearly related to the displacement of the object. So a mass on a spring is a great example of something that oscillates in simple harmonic motion because the spring force is going to be directly proportional to the displacement. And that occurs, we know that because of Hooke's law, F equals kx. So I don't know if you can hear Willow crying, but she's really sad to not be a part of this video anymore. So that's a really important thing to keep in mind. Let's look at our position versus time graph for our mass oscillating in simple harmonic motion on a spring. Now, to make an equation for this graph, we're going to start with the unit circle. If you have not yet learned this in math class and you haven't watched my optional videos on the unit circle and the cosine or sine function, please go back and watch those so this will make a little bit more sense. So if I have my unit circle, and I'm just going to put A here for the unit circle is technically 1, but that's okay. So we have the radius of A. If I have a theta here and I drop down so that I have my x coordinate or x component of this, then my x coordinate of that point is going to be this length of the line right here. And this is the radius, so that's the amplitude. So I could say cosine of theta is equal to x over a. And then I can isolate x and I get x equals a times cosine theta. So now when I apply that to this graph where I'm graphing it with time, I want to take my theta and put time in there. And we learned from our kinematics of rotational motion that my delta theta is equal to omega times time. So this is my change in position equals velocity times time when I'm moving at a constant velocity. I'm going to replace that here, and then I get x is equal to a times the cosine of omega t. And that is the equation for this graph. Notice that the coefficient in front of our cosine, that's going to be the amplitude of the curve. So that's going to be the maximum position that the curve gets to, and also the minimum position will be the same magnitude. So that's the amplitude. You will be taking the cosine of a term here, and it will have a constant, which is your angular velocity, times time. So whatever the coefficient of your time is, that's your angular velocity. Remember that angular velocity is equal to 2 pi times your frequency. It's also equal to 2 pi over your period. So 2 pi is how many radians you go through in one rotation, and period is the amount of time it takes. So delta theta over delta t equals omega. So I can rewrite this equation to say a times the cosine of 2 pi f times t, or I can also write it as a times the cosine of 2 pi t over t. Sorry, I ran out of board here. Notice here that when your time elapsed is equal to your period, then you're starting the cycle over, because we know that the cosine of 0 is equal to the cosine of 360, which is equal to the cosine of 720 and so on. So every time you make a full cycle, you're starting that motion over. And this is going to be a repeating thing in our equation and in our graph. All right, so now let's talk about the velocity versus time graph. When I draw my velocity versus time graph, we can use the things we learned from the first unit, where the slope of the position versus time graph is equal to velocity. So my slope is 0 here at the beginning, so I'm going to have 0 velocity. Then my slope is negative, and my slope is 0 again, and my slope is positive, and my slope goes back to 0. So my velocity versus time graph looks like this. Now this is a negative sine curve. So we would write our equation as v equals, our amplitude of this curve is going to be v max and basically negative v max, right, or v min. They're going to have the same magnitude, they're just going to be in opposite directions. So this is a negative sine curve, so I'm going to put a negative here, a positive sine curve would go up first, and then we have sine of, oh, definitely forgot my amplitude there, negative v max times the sine of omega times t. We can put the same thing in here because these have the same frequency. There's going to be a phase shift between them. They're going to be offset a little bit, but they have the same frequency. So if you are in calculus, you should know that the derivative of a cosine function is a negative sine function. So that should make sense to you. If you're not in calculus, you can figure it all out using the slopes. Not a big deal. Now let's talk about the, oh, sorry, I wanted to rewrite this again. V max times the sine of 2 pi f times t, and then I'm not going to write it, but you can also do negative v max times the sine of 2 pi t over t. So you can use the different equations for angular frequency to get whatever you need. Now, once again, this here is the amplitude of this wave. I'm going to tell you that the V max is equal to the amplitude of the position graph times omega. Now, if you are in calculus, it will be easy for you to see that because you know that when taking the derivative, your coefficient here becomes whatever this coefficient is times the coefficient of your time in the equation. So you just multiply those together, and that's what you get for your amplitude there. So our maximum, or V max is equal to A times omega. If you're not in calculus, it just makes sense with the units. So we know that we have to get a velocity here. So if we take amplitude, which will be measured in meters, and we multiply by omega, which is in cycles per second, but remember cycles is a real unit, so it's really per second. So then we just have meters per second, which gives us our maximum velocity. Then we are going to make our acceleration graph. And we can use the slope. So here the slope is negative, so we have a negative acceleration. Here the slope is 0, so it goes to 0 there. Here the slope is positive, it goes to positive, back to 0, back to negative. So that's our acceleration graph. If you're in calculus, you know that Willow taught you that the derivative of sine is cosine. So you have a negative sign here, take the derivative of it, and you get a negative cosine. And we write our equation, acceleration equals negative A max times the cosine of omega t. Once again, they're going to have the same frequency because of how they fit together, and we already talked about why they have the same frequency. And then we could rewrite this with our different terms instead of our omega. Also, our A max is equal to A times omega squared. And if you're in calculus, you know that when you take the derivative of your sine or cosine function to find out what this coefficient is, you're going to take the previous coefficient times the coefficient of time and multiply them together. So you get A times omega, and you get A times omega squared. That will help you figure out some things in your problems and also some relationships between your equations. I think that's it. Good job.